Alright guys, so I was assigned number 65 from homework 1.
So the problem says, on your first trip to planet X, you happen to take along a 200 gram mass, a 40 centimeter long spring, a meter stick, and a stopwatch. You're curious about the free fall acceleration on planet X, where ordinary tasks seem easier on Earth, but you can't find this information in your visitor's guide. One night you suspend the spring from the ceiling in your room and hang the mass from it. You find that the mass stretches the spring by 31.2 centimeters. You then pull the mass down 10 more centimeters and release it. With the stopwatch, you find that 10 oscillations takes 14.5 seconds. Using this information, what is G, or gravity?
So basically what this problem is asking, given a set of conditions, it wants you to, it gives you a mass spring system that's on a different planet, or planet X as they call it, and given that mass spring system, it asks you to find what the gravitational acceleration
is on that planet. So to help explain this a bit easier and let you visualize it, I drew a picture. So basically, at this top end of the dimension line, this is where the spring originally was. And then once we hung the 200 gram mass from it, the spring stretched down 31.2 centimeters. And then after that, we stretched the spring down manually even further by 10 centimeters and then let it go. So the mass is going to bob up and down until it goes back to equilibrium and then settle. All right, so as is with every problem, I like to write what I want and then what I know. So in this case, we're looking for gravity. We want gravity, which I'll use G for. And we know various things such as mass values are given in the problem, length values are given in the problem. We know force is equal to the spring constant times displacement. We know force is equal to mass times the gravitational acceleration in this case. We also know omega is equal to 2 pi over t, or angular acceleration is equal to 2 pi over t, and it is also equal to the square root of the stiffness, the spring constant over mass. Also, period is worth noting. In the problem, we're actually given period somewhat, but it's given in kind of a convoluted way. So it actually tells us that 10 oscillations takes 14.5 seconds, but we know that period is the time it takes to make one oscillation. So we're gonna basically just divide 14.5 by 10 and we'll get a period of 1.45 seconds. All right, so let's get solving. So we mentioned earlier that force is equal to the spring constant times displacement. We also mentioned that force is equal to mass times gravitational acceleration, which allows us to write kx is equal to mg and have it be true. And then we can then isolate for g, and we get g is equal to the spring constant times displacement over mass. So this is a good start because we're looking for g, and now we have an equation where g is isolated. The only problem here is that k is an unknown value, so we need to do a little bit more solving. So let's try and write k in terms of things that we know. So we can start here for that. We know omega is equal to the square root of k over m, and then we can isolate k, and we get k is equal to m omega squared. So now we have k written in terms of different variables. So we can substitute that equation into k in the former equation, and we get g is equal to m omega squared times x over m. Do some simplification, and we get this: gravity is equal to omega squared times displacement. So the only issue with that, again, this is good because we're looking for g. Now we have an equation for g, but we still don't know what omega is, so we have to break this down further. We know omega is equal to 2 pi over period, and we actually are given, as we mentioned, a somewhat convoluted, but nevertheless we're given a period in the problem. So we can substitute this in for omega into this equation, and we get g is equal to 2 pi over period, all that squared, times displacement. So this is an answer. We know it's an answer because we have what we want, gravity, written in terms of only things that we know. Again, the period is known because we did 14.5 divided by 10 earlier to get a period of 1.45 seconds. And displacement is just a unit conversion of the given value into meters. And yeah, once you plug everything in, you should get 5.85 meters per second squared, or around there, depending on how you rounded. I think the biggest pitfall with this problem is probably just starting it with visualizing it. Some people might think that this length that's given is the length of the entire spring, but it's really the length from the original, where the end of the spring originally was, not the length from the mast to the ceiling. And then over here, same thing, people might have some trouble visualizing. When they say you stretch the spring 10 centimeters, it is saying, the problem is basically telling us the equilibrium point is right here, at this little cross section, and we're stretching it 10 centimeters below that and letting it go. All right, that's about it. On to the next one.